Welcome to Land Eco Lightning Talks and Thinking Like a Landscape with Dr. Kevin McGarrigle. For this three-part series on working with landscapes, in part one, I talked about the importance of stating a clear pattern process question. In part two, this talk, I'll talk about the steps involved in formally defining the landscape. And in part three, I'll talk about the importance of landscape definition. Okay, let's get started. Recall from the first talk in this mini-series that asking a good question is hands down, invariably, the single most important step in any landscape analysis, because the landscape cannot be defined and the landscape analysis cannot be meaningful without a very specific pattern process question that ideally is specified in terms of a SMART objective. Once this specific pattern process question and ideally SMART objective have been identified, there are a number of steps involved in formally defining the landscape to guide the subsequent landscape analysis. I've identified 5 critical steps. Each of these steps is critically important. None of these steps can be skipped. And overall, these steps involved in defining the landscape are perhaps the most underappreciated, underestimated, and underrecognized part of the entire landscape process. Because without making clear and informed decisions about each of these steps, essentially you end up with garbage in, garbage out. These 5 steps are: first, choosing a conceptual and analytical model; second, selecting the thematic content and resolution; third, selecting the spatial scale, both grain and extent; fourth, dealing with fragmenting features; and fifth, considering the landscape boundary in context. And remember, each of these steps and the choices made at each of these steps have to be guided by a very clear pattern process question and a very specific SMART objective pertaining to that pattern process question. The first step involves choosing a conceptual and/or analytical model of landscape pattern. That is, how do we represent the pattern of interest digitally and put it into map form so that we can analyze that pattern and relate it to a process in a meaningful way. And it turns out that there are a number of common conceptual models and corresponding analytical methods that capture the major kinds of patterns in real-world landscapes that are typical in landscape analysis problems. In this figure, I've depicted several of them, including a point pattern model in which the features of interest are actually represented by points, even though they may not be physically point features. They may actually have area associated with them, but the interest here primarily is in the XY coordinates of those features and the number and the spatial arrangement of those features. So here we would call this a point pattern analysis. We're conceptualizing the pattern in terms of the distribution of point features, and we're analyzing the pattern in the distribution of those points and relating it to some process of interest. A linear network model is where we represent the pattern in terms of a network of linear features. So one might think about a stream network or a fence row network. And here we're primarily interested in these linear features and their density and their connectivity and how they influence some process of concern that either uses that network to flow along the network or is impeded by that network during flows across the broader landscape. Third would be the patch mosaic, in which we're representing the pattern by a set of categorical classes such that we can produce a mosaic of categories or a mosaic of classes that collectively portray the landscape as a set of patches, if you will. And this is clearly the most common conceptual and analytical model used in landscape ecology and in landscape problem solving, and the one that folks are probably most familiar with. Another conceptual and analytical model is the gradient or surface pattern model. And this is a model where we represent the feature of interest as a continuous process. So some ecological attribute that is continuous in nature, and that can at least potentially have a value at every location, such that we can kind of represent the pattern as a continuous surface. Common example being a topographic map looking at the elevation as a surface. And then lastly, just as an example shown here, this graph matrix representation, which is essentially a hybrid model that adopts aspects of the point pattern, potentially the linear network, patch mosaic, and gradient, and represents it in kind of a unique way that takes advantage of some mathematical properties of mathematical graphs to conduct some fairly sophisticated analyses. So the idea here is that there are these alternative conceptual models that correspond to a suite of analytical methods that are designed to deal with those kinds of patterns. And one must choose the model that is relevant for the specific pattern process under consideration. And in some cases, it's clear and obvious which model is the only or the most appropriate. In some cases, it's less obvious, and there are choices. And in fact, the same problem could be analyzed or could be addressed using two or more of these models. The important thing here is that one must make a decision at the very beginning of which of these models is going to be adopted, because the subsequent definition of the landscape and the formal analysis will all be guided by this conceptual model. The second step is selecting the thematic content and resolution. By thematic content, I'm referring to what is the ecological attribute or attributes that you are representing in your landscape. In this case, it's canopy cover, as shown in the figures on the right, and that is displaying a pattern in canopy cover across the landscape that presumably is relevant to the process I'm considering. And the thematic resolution refers to how many classes, in this case, of canopy cover am I interested in. If canopy cover is my thematic content, I have to decide how many classes, whether it's 3 classes or 5 classes in these two examples, and that is the thematic resolution. How do we choose the thematic content and resolution? Well, of course, it goes back to the pattern and process under consideration. One must identify the process and then hypothesize what is the appropriate thematic content for addressing that process and what is the appropriate thematic resolution. So, for example, in this case, looking at American marten habitat suitability, is the thematic content better represented by cover types, broad cover types, or is it better represented by several stage classes, or perhaps it's represented by a combination of cover type and several stages? That would be the choice of thematic content. And if I choose, for example, cover type as my thematic content, do I want to represent cover type with 3 classes or 9 classes? That would be the thematic resolution. Both of those decisions, what thematic content to choose to use and what thematic resolution, are critical for defining the landscape in a manner that's relevant to the process under consideration. The next step is selecting the spatial scale, both in terms of the grain and extent. So once we have decided on a conceptual model, and in this example, it's the patch mosaic model, and we've selected thematic content, in this case, the example being canopy cover, and its resolution, in this case, 3 canopy cover classes, we must decide on the spatial scale for representing that information. And in terms of grain, We must decide on whether we want to represent that information at a fine scale or a coarse scale. Do we want to represent each spatial unit of distinct canopy cover class, let's say at a 5-meter scale or at a 30-meter scale or a 100-meter scale? And similarly, we must decide over what spatial extent do we need to represent that information. And as in the previous steps, what guides this, of course, is the process under consideration. So in this case, for example, if we're interested in American marten habitat suitability, and once we have decided again on the conceptual model and the thematic content and resolution, we must decide on the spatial grain and extent. In this case, do we need to represent these cover type classes at the 15-meter resolution or at the 90-meter resolution or at the 150-meter resolution? And it's not always obvious what is the appropriate resolution, and there are methods by which one can determine which is the best resolution. But ultimately, one must decide on one or more resolutions for representing that pattern, because as you can see, even in these images, the quantitative assessment of pattern is going to vary substantially depending upon which resolution I choose. In addition, I have to choose the spatial extent. What's the overall geographic extent for representing the spatial pattern at this particular spatial resolution? And of course, that should be guided by the pattern process objective. And it's important to recognize that there's many aspects to the choice of the spatial scale of the analysis. It's not just the grain of the data over some specified extent, but there are other ways to change the spatial resolution. And without going into great detail here, just to represent a couple of examples of how one might adjust the spatial resolution in a manner that's relevant to the process under consideration, I'm showing you the original image on the left. In this case, a very simplified mosaic of canopy and non-canopy, but showing you a couple different ways by which one might change the spatial scale of the data without changing the grain or the finest unit of information. So in all cases, let's say the cell size in these images is the same. Let's say it's a 5-meter cell size, where we're representing for each 5-meter cell, whether it's canopy or non-canopy or open. But I can take that 5-meter resolution data, that's the technical grain of the data, and I could, for example, remove patches less than some specified minimum size. So we call this a minimum mapping unit algorithm, where we essentially identify the patches based on some neighborhood rule, usually whether it's cells are touching on a full side or whether cells are touching on a side or a diagonal. But once we've formed patches out of this mosaic, we then can drop all the patches less than some minimum size and essentially replace those with the nearest neighbor, or there's a variety of different algorithmic approaches for dealing with this. But as you can see, we've fundamentally changed kind of the spatial scale of the data by going from that original to this minimum mapping unit representation, even though the grain of the data is still the same. So we still have the same graininess, there's still 5-meter data, but we've kind of simplified the scale of the data by removing all the small patches. Another way to change the spatial scale of the data is with a kernel smoothing algorithm. And without getting into the details of what kernel smoothing is specifically, it's just a way to smooth your data, basically to take out all the roughness of the edges. And as you can see, you can have rather profound changes in the final pattern simply by smoothing the data. And there are multiple ways to conduct the smoothing operation. So even with just these two examples, minimum mapping unit algorithms and kernel smoothing algorithms, you can see we have lots of options for changing the spatial scale of the data, which ultimately lead to very different representations of the landscape pattern. The fourth step is dealing with fragmenting features. Fragmenting features are generally thought of as linear features that are potentially important in fragmenting or disrupting the process under consideration. So one might think of streams or roads or fence rows as linear features that potentially could impede the flows of ecological processes, or in some cases facilitate the ecological process under consideration. So in this example here, showing the same patch mosaic with and without roads superimposed on the landscape. And whether one incorporates fragmenting features into the landscape is entirely depending upon the process and whether that process perceives these features as fragmenting. And if they do, then it's important to incorporate them. If not, then it would just be unnecessary noise added to the landscape and essentially unnecessary. So in this case, I'm showing you a sample of a landscape where in the one case I've imposed streams as fragmenting features. So they essentially just superimposed on the landscape as its own unique class. But due to their linear nature, they primarily serve to break up the otherwise contiguous classes. Or on the right, I've incorporated roads as fragmented features in the same manner. Or perhaps in the center bottom figure, I've incorporated both roads and streams as fragmenting features. And again, whether it's important to include these or any other features as fragmenting features entirely depends upon the process and whether those are important to represent. The last step involves considering the landscape boundary and context, that is, the broader surroundings of the focal landscape. And the landscape boundary is important because one needs to know how open or closed the landscape is for the process under consideration. That is the boundary open to flows of the process under consideration? So, and if it is, then one must pay a lot of attention to the context of your landscape, the spatial context, what is surrounding that landscape. Because if the boundary is basically open to movements, then there's going to be a lot of interaction between what happens in the focal landscape and what happens around the focal landscape. And therefore, one needs to be aware of the characteristics of the landscape boundary and then potentially characteristics of what surrounds the landscape or its landscape context. So one usually thinks about the landscape boundary. Is it natural or is it arbitrary? If it's arbitrary, there's a good chance it will be open to the process under consideration. If it's a natural boundary, it may be relatively closed to that process, and one may have to pay less attention to what's on the other side of that landscape boundary. One also needs to pay attention to how different is the area outside the boundary. If it's very different than what's inside the landscape boundary, then one probably needs to pay a lot of attention to it because it may exert a lot of influence on the process inside the landscape. Again, assuming that the landscape boundary is relatively open. But if what's outside the landscape is very similar to what's inside the landscape, then the openness or closeness of the landscape boundary may be relatively less important. And ultimately, of course, one needs to consider how much the flows across the boundary affect the pattern and process inside. So if one's working with a process and a boundary that's relatively open to that process, and thus clearly the ecological process is flowing into and out of the landscape, it may be that that represents a relatively minor contribution to the overall pattern process relationship within the focal landscape. So for example, if the landscape is large enough and complex enough, it may be that these cross-boundary movements are relatively insignificant and can be effectively ignored. If the landscape is, for example, relatively small or relatively simple in pattern, it may be that the landscape boundary and its context play an increasingly important role. So each of these things must be considered when formally defining the landscape. So think about back to the first talk in this series, where we talked about the importance of specifying a clear pattern process question and objective. And we illustrated the importance of this with two examples. One of the examples is stated here. And that was with the goal of restoring resiliency of ponderosa pine and mixed conifer forest to wildfire disturbance. And recall that we translated that overarching goal into a specific pattern and process. In this case, the pattern being the extent and configuration of fine fuels within stands and across the forest, and the process being wildfire disturbance and the risk of high severity fire, or alternatively Mexican spotted owl nest or roost habitat. And then, of course, we translated this pattern and process into a SMART objective. This step of formally defining the landscape requires us to take that pattern and process and the specific objective and go through each of the steps of defining the landscape and make a decision, choose the most appropriate representation that will meaningfully address that pattern process problem. So for example, with this particular pattern and process, we need to choose a conceptual model. And while several of them are potentially suitable, one might easily choose the patch mosaic model for representing fine fuel patches. The thematic content is fairly clear here. It needs to be fine fuels, and the resolution being how many fine fuel classes are relevant. And perhaps here we could get away with as few as perhaps 3 from low to high loads of fine fuel, or perhaps as many as 6 or even 9 classes of fuels, depending on how finely we want to resolve our classification of fine fuel loads. The spatial grain here could be anything, but if we were concerned with how fine fuels affects individual tree level mortality, if we're not concerned with the individual tree level mortality and we're concerned in general with fire severity patterns on the landscape, we could probably get away with a fairly coarse grain here, perhaps 30 meters, 50 meters, or 100 meters, or even larger, to represent kind of coarse patches of fine fuels across the landscape. The spatial extent here is more or less being defined by the goal here, or by the pattern and process. In this case, it's defined by the extent of the forest, whatever that may be. And fragmenting features, we have to decide whether there are any fragmenting features, such as roads and streams, that would be important to the process. In this case, for example, wildfire disturbance and the risk of high severity fire. And since fire behavior is a contagious process, meaning it spreads spatially across the landscape, it's reasonable to think that features such as roads and streams could actually disrupt the spread of fire and thus be important fragmenting features in the fine fuel mosaic that would be important to represent in our landscape. So we'd probably want to include some of these features. We may decide to include only the larger streams and the larger roads, but that would be another choice that would have to be made. And in terms of the landscape boundary and context, clearly, almost regardless of how we define the landscape, but certainly if we define it based on the administrative extent of the national forest, the landscape boundary would be relatively open to the process of fire. That is, fire could relatively easily spread onto and off of the landscape across that landscape boundary. But the question we'd have to ask is for the extent and the complexity of pattern that we're representing within that extent, can we effectively ignore that boundary and its openness to the process and still make meaningful conclusions about the pattern and process within our landscape? And if our landscape was sufficiently large, and probably could argue that we could meaningfully look at how the fine fuel mosaic affects wildfire behavior across that forest without considering too much about what's going on outside the landscape boundary. All right, so the take-home message from today's talk is that without a clearly justified landscape definition, it's essentially going to be garbage in and garbage out. It's not worth conducting any landscape analysis until one has very clearly stated a pattern process and specific objective and translated that into a formal landscape definition in which due diligence has been given to each of the steps that I've outlined in this presentation. And because there are myriad ways to define the landscape based on alternative conceptual models, choices of thematic content and resolution, choices of spatial grain and extent, or alternative methods for rescaling the data, and incorporating fragmenting features or not, there are myriad possibilities here. So choose carefully the landscape definition to reflect the pattern process. Well, this is Dr. Kevin McGarrigle signing off from this episode of Landico Lightning Talks. I hope this talk has been helpful, and I hope you join me for my next Lightning Talk. In the meantime, keep on thinking like a landscape.